Hello and welcome, ladies and gentlemen. We are looking at activity 3.3. We are in packet 3, and we're just going to jump right into it. We have this little paragraph that says, in a previous activity, you constructed a square given its side lengths, or given a side length. Let's now consider how to inscribe a square inside a circle. One way to create a square is to use transformations. So, question 1 here says, and I know it's really light, like I said, this is a printer error or whatever. If you are following along in your packet, you should be good to go though. Number 1 says, circle B contains a right triangle, triangle ABC, which points A and C, or with points A and C on the circle and point B at the center. Describe each element using a term associated with a circle. So what this means is we're using our vocab that we learned about circles, and we're describing each of these things. So I'm looking at angle B here. So I want to look at angle B, and I want to say what this is in terms of a circle. Well, I know that it's an angle, okay? So we learned about a bunch of different kinds of angles. But I can go ahead and cheat a little bit and already write angle. Now I just need to decide what type of angle it is. Well, if you remember, we had 3 kinds, and we could tell by where their vertex was. We had one angle with its vertex in the center, we had one angle with its vertex on the circle, and one angle with its vertex outside of the circle. So the one with its vertex in the center was called a central angle, which means that angle B here, because its vertex is in the center, would be a central angle as well. So now we're looking at line segments BC and BA. So BC is this bottom one, BA is this up and down one right here. We're looking at these two things again. We're thinking in terms of a circle. So I'm thinking of a line segment that goes from the center to so a line segment whose endpoints are at the center of a circle and on the circle. And if you remember that those are called a radius, and since we have multiple of them, they are radii, or radiuses if you prefer that. This is the technical term for it. And now we'll look at line AC here, line segment AC. So we see that it's a line segment, and in terms of the circle, okay, it has endpoints both endpoints are on the circle. We constructed about 6 of these in the last activity when we made it in a hexagon, an inscribed hexagon, and that would in fact be called a chord here. Okay. If you remember, a chord is a line segment inside of a circle, with both of its endpoints on the circle. Okay, so now 2 here says that use patty paper to rotate the right triangle to create square ACDE. How do you know that all 4 vertices lie on the circle? So I unfortunately don't have patty paper. I can't do the rotations here. If you were to do it, what you would do is you'd trace your patty paper. So I'd hold my patty paper, I would trace over the triangle, and then what I would do is I would rotate it 90 degrees, and then I would trace, then I would draw this triangle, right? And then the one that was up here would still be hanging out, and then you would trace this, and then you would rotate it again another 90, draw that one, rotate it one more time, and then you should have something that looks like a square. What I'm going to do, because I don't have patty paper, and another way that you could construct this square, okay, is I'm going to use the lines that I already have. I'm going to use the lines that I already have and do this action. I apologize about the shadow on this one. I know that it can be kind of tough to see. Okay, I'm going to do this, and then now I'm just going to connect my endpoints that are on the circle here. Okay, so this is another way that you can do it. If you want to do it with the patty paper, that's obviously what they would like you to do. I would like for you to do it that way as well. Either way, you will get a square, and you will be good to go though, so whichever you really choose, it's kind of up to you. So there you go. So we have this square now. And so it said that it was going to be square ACDE, so I'll go ahead and label it that way, so ACDE. And it says, how do you know all 4 vertices lie on the circle? That's the second part of question 2. Well, we said that line BC and BA were both radii, okay, which means that they are the same length, and also that they have one point on the center, one endpoint on the center of the circle, and one endpoint on the circle. So because I rotated these, and because I kept point B always in the same place, if you're using the patty paper because you rotated them, or because of me you copied them, right, I know that line BD and BE are also going to be radii. And so because that is the case, that means that the radius BD is going to have one endpoint on the center of the circle and one endpoint on the circle itself. So D would be on the circle, and then same over here, E would also be on the circle. So how do you know that? You can just say that in some kind of words there. A shortened version would be BD and BE. Those line segments are radii. Boom, that's one way that you can do it. Okay, moving on to number 3 now. Okay, number 3 says verify that you created a square inscribed in circle B. To do this, you need to show that all side lengths of the square are equal and each interior angle measure is 90 degrees. So part A says show that all side lengths are equal. Suppose that BC, so the length BC is equal to X. Determine each side length of the square, label each length. So what I'm doing now is I'm assuming that the length of this, I'm not actually measuring it. I'm just going to go ahead and say that this is length X. Okay. And I want to know what the length of AC is in terms of this X value. So what I'm going to do here, so we said that BC is equal to X, okay? And so over here we have a little reminder on the Pythagorean theorem, A squared plus B squared is equal to C squared. So what I'm going to do here is I want to know the length of AC because I want to prove that this is a square, so I need to prove that all of these lengths are the same. So one thing that I can do right away, BC is a radii and it has length X, so I can go ahead and say that all of these other radii in the circle have length X as well. So then now I'm looking, if I want to find this, it's going to be A squared plus B squared equals C squared. So X squared plus X squared is equal to this, the length of AC, right? So that means that X squared plus X squared is equal to AC, the length of AC squared. So then if I look at 2x squared, right, because x squared plus x squared, I have 2x squared. So 2x squared is equal to AC squared. And then if I were to square root both sides, okay, I would end up with a rad 2 times x is equal to length of AC. Okay, so then x times rad 2, I'm just going to rewrite it this way. It's the same, right? Because here I have 2 times rad x, or rad 2 times x, excuse me, which is multiplication. And we know with multiplication, it doesn't matter what order we do it in. We can flip-flop those any way we like. So then I'm just going to write it over here as x times rad 2 because that is a little bit easier, okay? A little easier to see at least. So then all of these lengths are going to be x, wow, I cannot write. So this one is also going to be x rad 2. X rad 2 and x rad 2, and the reason that that is because all of these a, so when we did a squared plus b squared, it was x squared plus x squared. Well, since all of these radii are equal to x, then I know that all of these diagonals, all of these diagonal lines that we drew here, all of these chords are also going to be equal to x times rad 2, because we would find them the same way. I'd go x squared plus x squared is equal to this, x squared plus x squared is equal to this, x squared plus x squared is equal to this. Those would all give me the same length. So I have my lengths. It says determine each side length of the square, label each length. We did that. And then B says verify that each interior angle measure of the square is 90 degrees. So we had the Pythagorean theorem, this top part that we used for this question. So now for part B, I want to look at the bottom part of this. It says the converse. So the converse, we'll talk more about that later, okay, but we're just going to go ahead and leave it for now. The converse of the Pythagorean theorem says that if a squared plus b squared is equal to c squared, then the triangle is a right triangle. Well, we just used the Pythagorean theorem to find this length, so I know for a fact that with this length, a squared plus b squared is equal to c squared, okay? So we can go ahead and say for sure that that a squared plus b squared is equal to c squared, which means that this triangle ABC is going to have a 90-degree angle in it. We also know that CBD would have a right angle in it. We would know that DBE, that would have a right angle, and that would have a right angle. Okay. So B says verify that each interior angle measure of the square is 90 degrees. So all this does for me is tells me that these are all right triangles. Okay, but if you remember right triangles, so the interior angles of a right triangle, or of any triangle, excuse me, the sum of the interior angles of a triangle is 180 degrees, right? And I know that in a right triangle, I have one angle that's 90 degrees, so then I have 90 degrees left, and I have two other angles that are both equal to each other, okay? Well, at least, shoot, I'm trying to think of a, oh boy, I was trying to, oh, here we go. Okay, we're good. Sorry, I was trying to think of the right conjecture to use, but here I got it. So we know that this is a right triangle, so I know I have 90 degrees left to use. We also know that this triangle is an isosceles triangle because it has two side lengths that are the same, x and x. Okay, and we know that isosceles triangles have two angles that are the same measure, and since I can't have two 90-degree angles, I know that my two angles that are left have to be half of 90, and half of 90 is 45, so they would both be 45. So that means that 45 degrees here, 45 degrees there, 45, 45, right? And so on and so forth. And so 45 plus 45 is 90 up here, 90 there, 90 there, 90 there. So all the interior angles of this square that we created are also 90 degrees. Cool. Okay. Here we go. So now part 4 says consider line segment AD and line segment CE. So AD is from this tip top here to the bottom, and CE is this diameter that is across here. Okay. And it says describe each line segment in terms of the circle and in terms of the square. So I actually just gave it away there. In terms of the circle, these lines are both diameters. Okay, if you know what a chord is, so a chord is a line segment that is on the inside of a circle with both of its endpoints on the circle. A diameter is a special type of chord in the sense that it is also a line segment with both of its endpoints on the circle, but it cuts through the center of the circle. Right, so AD, A and D are both on the circle, and it cuts through the center B. C and E are both on the circle and cuts through the center B as well. So those are both diameters. In terms of the square, though, these are called something else. And if you'll remember, okay, so maybe it would help if I oriented my square like this. These are called diagonals because they connect opposite corners of this square. They're called diagonals. So in terms of the square, they are diagonals. Perfect. Okay. So now part D here, or excuse me, part B says describe the relationship between AD and CE. So describe the relationship between these two things. And so this is a throwback to the packet we just finished up. It's asking us what's the relationship between the diagonals of a square or between the diameters of a circle here. So if I went with what's the relationship between the diameters of a circle, I would say that they're congruent. Okay, but that's all that I would know. And I want to be really specific here. I want to describe the relationship as accurately as possible, as in-depth as possible. So if all I get from the circle is saying that they're congruent, then I want to look at the diagonals of a square and what I know about those. Well, if you look back to your table from the last packet, we would know that the diagonals of a square are congruent, they're perpendicular, and they bisect each other. There we go. Right? Which makes sense. So if I look at all those things, okay, congruent, diameters of a circle are always congruent, because at least of the same circle, diameters of the same circle are always congruent, so that checks out. Perpendicular, we already said that all of these were 90-degree angles, and we know that when two lines cross each other perpendicularly, they create these 90-degree angles in here, so we're good there. And then they also bisect each other, which means that they cut each other directly in half. So if the length of my line CE is x plus x, that means that the length of my line CE is equal to 2x. And so 1/2 of that, if I were to cut the line CE in half, would leave me with one side with length x and another side with length x, which of course we have here, and then same with the top and bottom there. So they do in fact bisect each other as well. So there you go. Okay, we have one more thing here. Yeah, one more thing. Okay, so we have this big, huge circle right here. Almost takes up my whole screen. Question 5, it says, use diagonals to construct a square inscribed in circle O. Describe your process. So first thing you want to do is construct it, and then you want to describe it. And I'm just checking, okay, yeah, the next thing is 3.4. So this is our last one in 3.3 here. So use diagonals to construct a square inscribed in circle O, and describe your process. Okay, so I'm going to do it first, and then I'm going to describe my process. Okay, and if you guys, I guess actually I'll describe it as I do it. So I'm going to have process down here. Okay, and then so I'll just do some sliding. Okay, so the first thing I did was construct a diameter of circle O. That was the first thing. And I want you to know, this can be any diameter. I did mine across from left to right. You can do yours up and down. You can do diagonal. You can do any kind of crazy thing that you want, okay? This was the first thing that I did, okay? So then the next thing that I'm going to do, this one's going to be kind of hard, and I apologize that that the circle is so stinking big. It makes this kind of awkward. And also, because it's such a big part of my screen, it makes it hard for me to center it and keep it where I'd like to keep it. Okay, so now second thing that I'm doing, and I'm not quite done yet, so I'm not going to go to process, but second thing I'm doing is constructing a perpendicular bisector. Okay, so then, so thing 2 Oh, I don't want to be on the screen down here. So 1 was construct a diameter, any diameter of circle O. And then part 2 here was construct, oh, I guess I could name this diameter just to be really fancy. So I constructed this diameter AB, and then I'll construct a perpendicular bisector of AB as a diameter. I'm just trying to think of the best way to say it. So I constructed this perpendicular bisector, awesome, but then I wanted to say, but I constructed it as a diameter of circle O. And there's probably a better way that you can say that. But I constructed a perpendicular bisector of AB, which I did. That's what these arcs were, right? Perpendicular bisector as a diameter of circle O, which means that I had both endpoints on the circle. And then I would say I can named CD, right? So I can go, I can say that this top one is C, and this one's D, and so now I have that named CD. So now I have my diameter AB, my diameter CD, that is also a perpendicular bisector. And then part 3, connect sequential points, or consecutive, that's the word that they've been using. I was trying to remember. Consecutive points on circle to create square ACBD. And I messed up because if I really wanted to make this ABCD, I would have gone AC and then BD, and then I could have gone ABCD, but because I goofed up, we'll go ACBD for our square. So then now the last thing, okay, is just to connect these points here. Once again, I apologize about the shadows on this. I'm not sure if there's ever a way to get perfect lighting unless you're like, you know, PewDiePie or Ninja or Summit or someone that has a lot of money and isn't paying off student loans. There you go. So there you go. There's our square. And then that was the last thing I did to construct it. You could do some things to verify it, but as far as just building the square itself, that is all we did there. And then you could mark these as 90-degree angles if you wanted. You could say that all these have the same length X. You could label it any way you wanted. But as far as the construction, you just need these things. There you go. So that is the last part of 3.3. Oh, also, it has this little, sorry, really fast before I run away. It is an inscribed square, a cyclic quadrilateral. This is just something to think about. And you can see that it said think about, but the think got cut off because poor printer. Anyway, is an inscribed square a cyclic quadrilateral? Well, if you remember, a cyclic quadrilateral is a quadrilateral who has all of its vertices on that lie on a single circle. So I have a single circle here. All of the vertices lie on the circle. So I would say yes, an inscribed square is a cyclic quadrilateral when it is inscribed on a circle, right? Because you could have a square, so really fast, kind of getting off here, but if I have a square that's inscribed in another square, actually, yeah, our answer would just always be yes. If you remember that squares, so we said that cyclic quadrilaterals have opposite angles that add up to 180 degrees. This will always be the case for squares because squares always have 4 90-degree angles, which means that the opposite angles will always add up to 180 degrees in a square, which means that every single square you've ever made in your entire life is a cyclic quadrilateral. You just didn't know it. Anyway, that's the end of 3.3. I hope you all have a wonderful evening. You're wonderful people. I'll see you in class. Let me know if you have any questions, and I will catch you guys on the flip side. Adios.